Back. Thank you for attending our second session, both those attending in person and those who have joined us on Zoom. Once again, sorry for repeating myself for those that have heard. My name is Pat Kern. I'm Sustainability Policy Analyst for Albany County. This is our second clean energy training of the day. Once again, we're just really excited about a lot of the initiatives that the county executive is pushing for in terms of sustainability and climate change. And this is just a small piece of that. So once again, thank you for joining, and I will kick it off to Chris.
Great, thank you. My name is Chris Doty. I've been an engineer for about 11 years, and I'll be presenting the Understanding Solar PV Permitting and Inspecting in New York State course here today. There's a lot of material to cover, so we'll be moving through pretty quickly. If there are questions for the people that are here, we just save it till the end. We'll go over questions at the end. For people on Zoom, you can put your questions in the chat. We'll get to those at the end. And then kind of the main purpose of this presentation is to give kind of a 10,000 foot view of the unified solar permit and the inspection process, and go over sort of more common errors that are seen during inspections. It's not really to give an answer to every single specific issue you may see during an inspection, because that would take many, many hours. But if you do have specific questions, you can contact me. Here's my contact information, or you can contact NYSERDA, and we can get the question answered for you. All right, so this course is, like I said, solar PV permitting and inspection course. It is approved by Department of State for 2 hours of in-service training credit, one for enforcement and administration, one for uniform code. For the people on Zoom, the people who are on are all set, but you have to sign in within 15 minutes of the start of the session, and you have to log out at the scheduled end of the section to 30 minutes after, in order to get credit. Also, the Department of Building Standards and Codes will give you credit if you're not, actually paying attention. So you have to keep the Zoom window as your main screen throughout the whole presentation, or else they won't give you credit. All right, so during this course, we're going to review the New York State Unified Solar Permit, or USB, that was created by NYSERDA. It's a model permit that helps permitting authorities across the state. We'll then go kind of into what to look for on field inspections, what labeling is required, and then we'll look at a bunch of common errors that are seen over many, many inspections that NYSERDA has done. And also there's a number of questions throughout the presentation. So obviously the people that are here can just answer, or if you are on Zoom, you can just put your answer in the chat. I'll leave a minute to kind of think about it and put the answer. All right, so New York State Unified Solar Permit. Over 300 communities in New York State have adopted the Unified Solar Permit. It's an easy process. It can be done by a local law or adoption by a local government. And the Unified Solar Permit is kind of a best practice, and it includes requirements that can be applied to solar PV systems of really any size. It was made originally for residential, and it says it's applicable up to 25 kilowatts, but it can be, the requirements can be applied to any size system. So it's a great resource for permitting of solar systems. All right, so what's it about? The Unified Solar Permit is a streamlined, standardized, comprehensive tool you can use to kind of expedite your approval process for installing solar in your community. It enables you to be very consistent, predictable, and repeatable in what you require for permitting. using the unified solar permit can also save you money and time and, help move through much more quickly. First, we're going to go through the application. So this is the first 2 pages of the application. It's basically just kind of a cover sheet. It has not a lot of technical information, which will come later, but it's more of kind of a who, what, when, where, and why of where the system will be and what the permitting authority can expect to be there. So the first thing on the first page is to determine if you're eligible to use the permit. There's 6 questions. If you can answer yes to all of them, then this permit is applicable to your situation. Things like if it's less than 25 kilowatts, like I said, or if you need a historical review or a special permit, or kind of how the system will be installed. And also down on the bottom here, there are sections that the permitting authority can customize to their specific needs. So it's not just you download the permit and you're stuck with it. You can adjust it to require exactly what you need for your jurisdiction, and that way it's more useful for you. So here's another section. This is kind of a section that describes the submittal requirements for the applications. Here's one of those situations where you can customize the fields such as the fee schedule, the payment methods. You can list your website and your email address so that contractors and homeowners, whoever needs access to this information, has it in one place and they know where to get it. And it's very useful to put everyone on the same page. Yeah, so it's a good place to consolidate all the information in so that everyone has all the same information. All right, so the third section down on the first page is where approximate timelines are spelled out of when contractors can expect to hear back on a review of their application. There may be different timelines for if it's reviewed and denied versus reviewed and approved. You may have very obvious errors or missing documentation that you need. That would likely allow the permitting authority to deny your application very quickly, so that you can adjust it and resubmit it. But to go through the whole application and verify that everything is correct, it may take time. So it may be a different timeline for that. And this is important because it gives solar contractors a clear expectation of when they'll hear back from the permitting authority. It's not just hanging out in limbo with them just waiting and waiting and waiting to hear. All right, so here's the first section of page 2. It includes very standard information. It's got the owner, the dwelling information. You see this on all types of permit applications that you would have to submit with the jurisdiction. It also has information for like your section block and lot number that would be on your tax map. And this is so that the authority having jurisdiction can easily locate the property that is where the system will be, and make sure everything is going to the right place and all the information is correct. All right, so the next section is very concise, and it gives a clear snapshot of the system that you'll be installing. It includes the basic size in kilowatt hour or kilowatts DC, which is how solar systems are typically talked about. It will also have the type of inverter and the location of the interconnection. So there's basically 2 types of interconnection. It's supply side and load side. Supply side is ahead of the main disconnect, and the load side is on like the home side of the disconnect. So it's typically a backfeed breaker or sub panel. And then it also has, like I said, the type of inverter. It could be a microinverter, string inverters, or DC optimizers. Knowing these three pieces of information basically gives the inspector or the code official to the ability to know what's going to be on site generally. Like there's going to be specific situations for each of these, but generally you'll be able to know what to expect when you get on site if you know these three pieces of information. All right, so the next section is detailed contact information for the solar contractor and the electrician. It should include licensing numbers for them where applicable. And it's important to notice down here, there's two signatures required. It's for the property owner's signature and the contractor. So you want to make sure that both are signed so that you know that's them attesting to the correctness of the information in the application. All right, so here you can see after these first two pages that are basically the application, it lists a whole bunch of documentation that's required for the permitting authority to review so that they can issue the permit. As you can see, it's 3 pages of sensitive information. It's to be compliant with New York State laws. They're basically construction documents, electrical documents, things of that nature. And all of these requirements would be the same for a small system like you find on a home, or up to multi-megawatt system. So this unified solar permit provides a lot of information that you can apply to systems much bigger than what it was specifically made for. And some of for the larger systems, some of the fields or some of the documentation needed may not be applicable, but it's a good framework for what you're going to need. All right. So part of this is, like I said, there's customizable fields. The permitting authorities can insert information on if you need separate inspections or permits in order to be able to install solar at your home. For instance, if you need a separate electrical permit or a building permit or a mandatory planning review, things of that nature. And this is kind of an opportunity for the permitting authority to customize this standardized unified solar permit so that they can get the information that they need to evaluate the system in their jurisdiction. The solar permit provides a good framework with listing everything that you need, but like I said, you can customize it to fit your specific needs. All right, so like I said, there's construction documents that are required as part of this process. We'll go through these in greater detail, but the most important thing to keep in mind is they have to be stamped and signed by either a New York State registered architect or a New York State licensed professional engineer. This is that professional taking responsibility for the quality and the accuracy of the design. Also for specifying the equipment. It's not really the code official's job to specify equipment for all these installations. And you should not be taking on that responsibility, right? If it's not stamped and signed and you issue a permit, that's sort of you attesting to the correctness, and it's sort of you taking that on your shoulders, and you should not be doing that. That just kind of opens you up to more liability, and it's not your job to take that on. All right, so now we'll go through some of the documents that we'll be looking for. Different documents have different things that we need to check. So first, we're going to go through the electrical details. And like the main thing to look for with this is you want to go through each of these items that are on this checklist in a methodical way so that you don't miss things. And the more you do it, the faster you'll get at it, and it'll be very easy to go through sequentially and make sure that everything is up to code and specified correctly. So basically what you want to do is you want to go through from either the array to the utility interconnection or backwards, and just make sure every item is accounted for. We'll go through all the different main components of the system in a couple minutes. Next, we have a roof or a site plan. This is a detailed plan that has basically the location of all the major components and rooftop access setback requirements. It's very important for to make sure everything is code compliant and follows the rules that it needs to. And it labels where everything can be found. And we'll go through that, like I said. And then lastly, there's the structural information. This is very site specific. No two buildings are the same and no two solar systems are the same. So everything in here will be, and specifically in the structural information, also for these other documents, but specifically for this, it's very site specific. It has load calculations to make sure that the roof can handle the load for the PV panels, all of that. So you want to make sure that all of these calculations are labeled and correct for the structure that it will be in. And there are checklists for all these, which we'll go through in a little bit. All right. So the kind of the whole point of the unified solar permit is to clarify the items that are required for the inspection, so there's no surprises, right? You don't want a contractor to not have the documentation they need to know what's going to be inspected and come back and be like, well, this wasn't listed in the requirements. You want everything to be kind of standardized and make sure everyone knows everything that will be inspected and the quality that's necessary. And so as the inspector, you'll be looking through and making sure that everything is code compliant, that the construction design documentation matches what was actually installed, and we want to do it, like I said, in a systematic way to kind of reduce human error. One thing to note is NYSERDA does require for systems that they incentivize, which is almost all, if not all, the solar installations in the state. They do require that photos be taken throughout the installation. This is very helpful for local inspectors, and it's important for reasons we'll get into later. All right, so people on Zoom, if you want to put in your answer to this, it's which item is not a requirement of the solar PV permit application? Site drawing, a wiring diagram, proof of payment of property taxes, or contractor's telephone.
Replay two, and vote C.
Whoa, can't believe you got it right. Yes, the answer is C. You do not need proof of payment of property taxes. All right. So now that you've received the permit package, could be your standard package that you use in your jurisdiction, or it could be the unified solar permit if you've kind of opted into using that. Now we'll kind of go through the tools in the section, or all the tools that will help you to review this permit package. And one thing that I forgot to mention in the beginning is if you are on Zoom and you want to get Department of State credit, put in your New York State training ID in the chat so they can mark that down. I forgot about that. All right. So now that you've received a permit package, now what? NYSERDA has many tools that they've developed to assist permitting authorities in their work. There's a design review checklist. There's the field inspection checklist, and there's a quality assurance checklist. All these can be found on the NYSERDA website, and they're basically designed by professionals who've done these inspections and literally thousands of inspections, and they outline what needs to be done for these inspections. And they're very comprehensive tools. They're very useful. And a lot of this can be found in the New York State Solar Guidebook, which is also available through NYSERDA. And we'll take a look at each of these in detail. And here's the guidebook. And you can add this this URL, which I believe I've supplied a copy of this, but if not, I will. So then everyone who's attending has it. All right. Like I said, all of these are available through NYSERDA. We'll go through the design review checklist and kind of its three main components, which is the requirements for the site plan, the electrical diagram, and the structural analysis in a moment. And all of these have to be looked at very thoroughly to determine if the system is code compliant. Like I said, they're available in the guidebook, and they have code references included, which is very handy when going through doing the inspection. All right, so the site plan. This is basically kind of a walkthrough of the components that are going to be installed at the site, and it gives the locations and kind of basic information of what will be at the site, including setback requirements and any trenching that'll be needed, things like that. So it's sort of to help avoid having to remove and replace a lot of equipment if it's installed like too close to the property line or something. It's so that you can avoid those mistakes in advance instead of, like I said, installing it and then having to take it all back. So here's an example of a site plan. It's not a perfect site plan, but it's a plan. It gives you kind of, like I said, it shows you the location of all the different components. You can see here the location of the modules. There's the interconnection, kind of the property line, all that. It'll tell you where the inverters are going to be, where the utility meter will be, if there's rapid shutdown installed with it, where the initiation device is for that. Should show you where there's rooftop access or ventilation. And one thing to keep in mind for this is you want to make sure that there's the professional designer stamp on the drawing. All right, so next we have the electrical checklist. This is a very important one because obviously electricity is dangerous, and if you don't go through all these in kind of with a fine-tooth comb, that could end up causing injury or hurting someone. So you want to take some time to go through all the items on this checklist, make sure that everything is accounted for on the electrical drawing, and you want to kind of look at them side by side if you can, to make sure everything is accounted for, and that way there won't be some bit of safety equipment that just gets left off. You want to keep track of what's there and what's not. If there's something that isn't there, you want to double check it during the inspection, and kind of go from there. So one thing to keep in mind here is that there may be a difference between kind of a code violation and a design review violation, I guess. Like a design issue, maybe if a disconnect switch or something is not labeled correctly, but it's not really a code violation unless it's actually on site that it was installed incorrectly. So keep that in mind. On this particular one, it looks like rapid shutdown hasn't been accounted for. That's a requirement in the code. So you'd want to check that when you got to the site. And you want to kind of note missing items such as different conductor sizing. If something is labeled but is not really applicable for the system, you want to keep track of that, and it kind of makes it easier for you when you go through at the site and you're doing the inspection. You can spend more time on things that were identified as problems in the checklist, rather than going through every single specific component and taking forever while you're on site and not being able to have the time to look into the problematic parts. Whoops. I forgot about that.
The annoying animation.
Yeah.
The next version.
So yes. So as you can see, this kind of, you can see here, it allows you to go through in sequential order, make sure everything, all the calculations are there, all the equipment is specified that needs to be there, make sure everything's done correctly. And there's no missing piece of information that would be necessary to evaluate the system. And so here we go with the structural analysis, the kind of the next section, or the last big section, I guess. And you want to go through all the items. The big thing to keep in mind here is down here, there's a bunch of calculations. I mentioned earlier that everything is site specific. This has to do with the framing of your roof and, if the roof will be able to handle the weight of the PV system, because they're not light. So you want to make sure that everything that your house can handle PV before you're, or the homeowner's house, obviously probably not your house. You want to make sure that they can handle that weight before you, approve the permit. And everything is site specific, like I said. All right. Again, keep in mind, one of the main things that you want to make sure is the case with these is it has to have the stamp of a professional engineer or registered architect. Like I said earlier, this is them taking responsibility for that design. You should not be taking that responsibility on your shoulders. It's their job. They should have signed and stamped the drawings. So make sure that that's there for sure. All right. So you have all the requirements that you need to issue the permit. The permit's been issued. Construction's complete. Now what? Now you have to go on site and actually do the inspection, right? So one thing to keep in mind is have you considered the safety of the inspection? So inspections are required to follow NFPA 70E, which is the standard for electrical safety in the workplace. And obviously OSHA requirements, everything needs to follow OSHA requirements, but NFPA 70E has been traditionally for specifically for electrical workers, but now it's been updated to include inspections as well. So inspectors have to comply with the standard. And as part of that, you have to do an initial risk assessment, make sure you're keeping in mind any risks that can be on site. Obviously for solar, there's a lot of electrical risk. That's kind of the primary thing that everyone will think of when you think solar, but there could also be risk if you have to get on the roof of falling or things like that. So you want to keep in mind those risks and evaluate if you need additional PPE to to be safe while you're on site. This is kind of the process you'll go through for the risk assessment. You go through, you think about all the potential risks on the site. You look at how you can mitigate those risks. Obviously, like I said, for solar, electricity is very potentially dangerous. So you want to make sure that you're establishing an electrically safe work condition. Probably not super likely for residential situations. You'll evaluate the likelihood of an arc flash incident. That can be fatal, so it's very important. And then if you do find that there is likelihood of that, then you want to choose arc related clothing. So that you can mitigate that risk as much as you possibly can. And so here is the hierarchy of controls. As you can see here, or hopefully you can see here, it's a little small here, but on the top here, that's the most effective of the hierarchy of control. That's just eliminating the hazard altogether. On the bottom is using PPE. Basically, it's just living with the hazard and hoping that whatever equipment you have will allow you to not be hurt by it. But obviously, you want to eliminate as many hazards as you can. That will allow you to be as safe as possible and kind of remove the hazard from anything you're even exposed to. And so many municipalities have gone to visual inspections only. And this basically is elimination in action, right? You don't have to get into the electrical panel. You can use photos, or if you can use other things and just visually inspect. You don't have to like actually get into things and open junction boxes and things like that. So you are removing that electrical hazard and you don't have to be exposed to it, which obviously makes you safer. All right, so question number 2. Which of these is not in the hierarchy of control for electrical safety? Sure, people on Zoom, but it's A, physically remove the hazard, B, isolate people from the hazard, C, reschedule work until after the normal working hours, or D, protection of the worker with PPE. Which of these is not included in the hierarchy of controls? Yeah. Obviously it's C. Hopefully it's obvious. Rescheduling the work will not remove the hazard. It will just delay it. So don't use that. And that would be a horrible idea. All right. So now we'll go through the field inspection checklist. This is provided by NYSERDA, as I mentioned. It's an extensive guide on what to look for based on over 4,000 inspections. It has code references in it. It's very robust and thorough, and it kind of gives you a step-by-step look through the inspection process. It's printable, so it's easy to print out, take into the field, and you can use it while you're on site. So it's super handy. Like I said, it's kind of an organized method to review the components of the system, start at one end of the system and move through to the other, basically from the array to the interconnection or backwards. It doesn't matter really how you do it, as long as you do the same every time. That way you'll get used to it. You'll know the components in order that are necessary. And it'll help kind of reduce human error. And so we'll go through basically the items covered in the checklist right now. So first is the array, right? This is the part that everyone sees, right? It's basically the panels. They can be installed in several different locations. You can have roof mounted, you can have ground mounted, or you can have pole mounted. That's obviously on the roof is roof mounted. This is ground mounted and pole mounted. Roof mounted can have additional challenges for inspectors. They could be on a steep roof, it could be very high up. You may need fall protection. It can be pretty difficult to inspect them. So you want to keep that in mind when you're doing your hierarchy of controls and your site evaluation. As you can see, ground and pole mounted are typically easier to see the connections. And you can get a much better view just of the system. So they may be easier to inspect, but I would imagine that roof mounted are going to be the vast majority of the inspections that you do. And so this, for roof mounted specifically, it's a great example of where construction photos being provided by the contractor are super valuable, because then you don't have to get up on the roof to, this specific situation has multiple arrays, you don't have to get up on all those different roof sections, make sure everything is up to code. You can use the photos, and that can be a big time saver, and it can also help make sure everything is safe. One of the things that you're going to want to keep in mind and definitely check for while you're looking at the array is make sure that the equipment that is specified in the design documents that you have already looked through is what's actually installed, right? You can make a design. I've seen many times where designs were provided and what's installed is completely different. So especially for electrical systems, everything kind of downstream from the array, specifically for PV is dependent on the electrical characteristics of those panels, right? So if you switch out the panels with a different kind of panel, you may have different amperages, you may have different voltages, and that could impact the conductors that you use downstream from that, and it could potentially cause an unsafe condition where there's too much amperage and the wire melts or something. And that could cause serious problems. It could cause fires. It could end up killing someone. So obviously, this is a very important section. You want to make sure that these match up. All right. So next, we're going to talk about the grounding of the array. This is super important. It's not only a code issue, but a safety issue. You have to make sure that the integrity of the grounding system is there's integrity of it from the array all the way down where it's grounded for your home, and it's really essential to the safety of the system. It's dependent not only on the conductors but also on the equipment itself, which can be used to carry fault current. And basically, it allows if there's a problem in the system, the current will go down through the grounding system, and it will not leave the system conductive and potentially dangerous. And if this is not done correctly, then like say this is a roof mounted system, if the grounding system is not installed correctly, you could have energized panels. Say you have to have someone go up on your roof to fix your chimney, right? And they touch the panel, they could get shocked by 600 volts potentially of DC voltage, and it could kill them. So obviously this is super important, and you want to make sure that there is a good grounding path through the whole system. Another thing is some of the systems now, a lot of them now, have integrated bonding, which is this is kind of an example of that. It can you have metal brackets that connect the panels together. This would basically be the grounding path that you would use throughout the whole system. So you want to make sure that those are installed correctly. You could also see ground lugs. As you see here, this is kind of more common for past installations. These are becoming more common now. A ground lug with a copper wire that goes through to every component of the system. And over here you can see that's obviously not great. It's a screw that's coming out. You want everything nice and tight and well put together to avoid problems down there. All right. Another thing to keep in mind is the contractor has to use outdoor rated components for the equipment. This is very important. You can see here, right here, they used a black wire tie. That's UV rated. That means basically it won't degrade in the sun. The white ones will. I've seen many times where The white wire ties were used outside, and in less than a year, they get super brittle and will just snap. So, if a white wire tie were used here, definitely before the 25-year life of the system, it would probably snap, and then these would just be hanging down on the shingles, likely getting rubbing, and eventually the wires would probably bend. Here you can see, it's kind of hard to see because it's small, but this screw that's used to hold the ground lug onto the conduit is rusting. So obviously it was not rated for outdoor exposure. Eventually that would just kind of deteriorate over time, and then the ground lug would just break right off. And then you don't have a well-grounded system. So as we've mentioned, that is very important. You want to make sure that the correct equipment is used to to install the system. All right, optimizers and microinverters, they're a DC optimizer is basically a converter that takes whatever amps and volts you have, and it conditions it to be what the inverter wants, right? So, and then a microinverter changes from DC, which is produced by the solar panels, to AC right at the panel, so that you have all AC voltage going through the conductors. Take a quick look at these. Basically, the checklist has specific sections for them. They're pretty similar. The requirements are pretty similar. Both of them, I believe, typically have rapid shutdown installed with them, which is part of the code. You need to have rapid shutdown installed with it. And another thing to keep in mind is for all of these components, right? Not just the microinverters or optimizers. You may have to look in the installation documentation for these things, make sure that they are, how they're supposed to be installed, so you can verify that they are indeed installed that way. And it can be mounting them or bonding and grounding. There can be a bunch of different things that can potentially be wrong, but you want to make sure that you understand the system so that you know if it's installed correctly. All right, so like I said, DC optimizers and microinverters have rapid shutdown installed with them. This is what rapid shutdown is. It's a method to shut down the voltage coming from the array at a place close to the array. The rapid shutdown may not be right at the array. Typically it's not. It's in a more easily accessible location, but that allows like a first responder or electrician, if they have to shut the system down so that they can have an electrically safe work condition. Or in the case of first responders, like if there's a fire, you want to just shut that off so that you're eliminating the hazard. All right, so question number 3, using microinverters and string inverters and DC power optimizers is one way to meet the requirement for rapid shutdown, true or false. What would you guys expect?
Yeah, what's in the thing?
What is?
What's in the thing? Anyone in the chat there?
So I think I mentioned microinverters and DC optimizers have rapid shutdown installed with them. And that is a valid way to comply with code for that requirement. So so you don't need to have a separate system installed for rapid shutdown if you have those installed with your system. Okay. All right. So now we'll look at the rooftop. The guidebook has a section for rooftop PV attachments and penetrations. In addition to making sure that you have to make sure that it's installed correctly. You don't want to have a situation where flashing was installed incorrectly or, penetration was done poorly so that you get leaks going into the house, causing damage. And so this section kind of has information on what to look for over here. This is kind of a weird picture, but you can, down would be that way. So, you can see that the flashing is installed correctly on this one. It goes up under the shingle so that the water sheds over it and won't, go back up under the shingle. Here we have a poorly installed rubber boot. This is the correct piece of equipment that you would use for this, but it was not installed correctly and it's pushed down. So, and over time you have water that pools in there and over the winter to turn to ice and it'll cause this rubber boot to fail. You would want it to be up so that all the water sheds right off of it. And so you would want to have the installer kind of reinstall that or fix it. All right, so question 4, properly installing roof flashings and ceiling roof penetration is a critical part of installing PV systems. Real problems. I think that it would be alarming if people get this wrong, I think, but obviously that's true. You don't want to cause the homeowner to have damage to their house and potentially mold and other problems. So yes, of course, you have to seal the roof penetration problem. All right. So next we'll look at junction boxes. If an enclosure is mounted on the roof deck, it has to be properly flashed, just like in the last section, and sealed so you can, so you won't have water entering the junction box. And also a metal enclosure, like you see over here. That has to be grounded because it's considered likely to be energized within the code. So that has to be properly bonded and grounded. Here that doesn't happen. You can really see it, but the green ground wires comes in and comes back out. It's not attached to this metal enclosure wall. So that would violate code. And then on the right, the box is non-metallic. It's just probably fiberglass or plastic. And that does not need to be grounded because it's not conductive. Obviously you don't need to ground that. And in both of these situations, the junction boxes have to be rated for outdoor environment, obviously, just like for all of the equipment that we go over. So next we'll talk about string inverters. This kind of is, you have to verify that the correct equipment is installed, and it's kind of vital to ensure that the actual installation matches the design documentation. All the conductor sizing is based on the PV array and the inverter. So if these are not what's in the design, then they can cause problems and cause amperage of wires to be too high, can cause melting wires, can cause a lot of issues. So you want to make sure that this is all in accordance with the design. One thing to keep in mind, so these are inverters, and here's the DC wiring coming down. So what happens is the DC wires come in, and then it gets turned to AC and it goes back out. DC wiring has to be in metal conduit, and it has to be labeled every 10 feet. And you can verify that the correct equipment is installed by looking at the nameplate, which is typically on the side of the inverter or underneath. Here we're looking at the conduit bonding. That's critical to having a safe installation. This is a plastic box. and it has metal conduit coming into it, so you have to make sure that the metal conduit is bonded to the grounding system. That way, if somehow a conductor touched the outside of this conduit, then it would not cause the whole conduit to be electrified, I guess. So you have to keep that in mind. If the junction box that you're looking at is non-metallic, you have to make sure that if there's metal conduit, that is bonded in the grounding system. Another thing, another thing to keep in mind is for PV systems specifically, there's PV rated fuses, which we in these. You have to make sure that the fuses used are PV rated, and for residential, it's up to, I think they have to be rated up to 600 volts DC, and for commercial, it's 1,000 volts. All right, some more on the inverters. Now we're going to look at the labeling requirements for the inverter. This one in this picture has a handle, a disconnect handle built right into the inverter, so you can just shut the system down right there. It has to be labeled as the DC PV disconnect. You can see right here. And it has to have a label showing that there's rapid shutdown installed. Just so if someone does have to shut down the system very quickly, they know where to go, they know how to do it. It's very important so that you can have a safe condition. All right. So next we'll look at the AC combiner. This is typically a kind of a junction box or a panel. What happens here is all the AC feeds from the PV comes into one single point, so it can be combined into one set of conductors before it's connected to the interconnect. So basically, you have all of these coming in here, all the power coming in here, and it goes out. There's black and red coming out, which would be what you would use to connecting into your panel or your utility unit. Let's see. Also, in this situation for the AC combiner panel, you don't want to have the ground and the neutral connected to each other. That is typically done in your electrical panel. So this contractor did an accurate job with that. That the white neutral you can see is not connected into the ground. So that's just something to keep in mind when you're looking at these things. Now we'll go through the different types of connections. This is an example of a load side connection. Basically, that's like when you connect the solar PV system into the home side of your utility meter, like supply side would be if it's on the other side of your disconnect. We'll go through that as well. But you can see the utility meter, power comes in, your connection for your inverter is on the home side of this connection. And what you need to keep in mind is typically you'll find a backfeed breaker for this kind of connection. That's a breaker in your panel that the inverter feeds power back into your panel from your PV system. And with this, there are kind of rules to follow to make sure that you're not exceeding the capacity of the bus bar and the conductors in your system. Basically what it is, it's what's called the 120% rule. You want to make sure that the sum of this breaker here, which say it's like a 20 amp breaker, to 18 amps coming in from your inverter. You have a 100 amp main breaker. You want to make sure that those are not this plus this is not greater than 120% of your bus bar rating, which is inside the panel. This is kind of technical, but that's mainly so you don't overload the bus bar and cause problems, with having too much current in the bus bar. So here's kind of an example. When you're looking at the load side connection, you need to look at your circuit capacity right here, which is max output current for each leg of the system. Typically, it'll be 240 volt. So 2 legs from the inverter. And you want to size the breaker and the wire to handle 25% of the rated output capacity for the inverter. So here we have 16 amp circuit. You want to just multiply that by 125%. You would use a 20 amp breaker and wire that can hold 20 amps. Conductor sizing is crucial for these systems because if you undersize them, like I've said, I think like 5 times, you can melt the wires, it can cause big problems and it end up with fires. And, I guess they're huge problems. So here's another example. The overcurrent protection has to be properly sized with the same system. You have 16 amps output, multiply that by 125%, and you get 20 amps. So you would want to use a maximum overcurrent protection of 20 amps. And like I said, most of the backfeed breakers are double breakers, 240 volt that corresponds to what's in the house. So you'll have kind of equal distribution on each leg. Here we see kind of the requirements for circuit identification. You need is part of the electrical code, just the general electrical code, not just solar. Then you have to have your circuits labeled. A lot of homes don't have that, like you're supposed to, and you want to make sure it's legible. This is, you can tell what it is, but it could be better. And another potential way to do that is to have kind of a map of, especially if you have multiple arrays, you can, this is a nice color coded map that shows where each circuit is going and what you would expect. And it's important to label things correctly and have them be easily identifiable and legible. So here's another kind of example, just to really drive home the point. It's a common load side connection calculation, just to make sure that the panel board is large enough to handle the PV system. Here you have the max current coming out of the inverter as 14.4 amps. Multiply that by 125%, like we've done the last couple slides, you get 18 amps. And then you have a main breaker of 100 amps. Your bus bar is rated for 100 amps. So this would be fine, right? As long as you position this breaker at the bottom of the panel, it should be fine. There should never be any situation in that panel where you would be supplying more than 100 amps to the bus bar. So you should be fine using the 125% rule. And that's typically why backfeed breakers are located at the bottom, right? If you have 100 amps coming in the top, and then you have, I don't know what you are doing in your house, if you have 100 amps coming in the top, but and then you have 20 amps coming from your PV system. At no point in that bus bar should you ever have over 100 amps, right? So that's kind of how that works. Next we'll go through supply side connection. This is the other type of connection. This is when the inverter is connected right in. So here's your service disconnect. This will be your panel. It connects in on the non-home side of the service system. So it's basically an additional service to your home that gets connected in. And these conductors right here, going from your inverter over to above your disconnect, They have to be 60 amps, and that's because they're considered an entrance conductor for the basically from the utility. You need to, per code, you need to have them be at least 60 amp rated. And you also have to have the disconnect be rated for basically new service areas. Question 5. Supply side connection must have a service rated disconnect switch with a minimum rating of
100 amps.
No.
Oh, wait, max. Oh, max. Oh, minimum, 20.
60.
It's not, but 60.
Yeah. So hopefully people in the chat said that. So it requires a minimum of 60 amps because it's essentially considered another service coming into the house, I guess. Some more on the supply side connection. You have to ensure that the connectors again are sized appropriately. To do this, you look at the inverter nameplate, you look at the max continuous inverter output current. Over here. For here it says 21 amps, sorry. So you would multiply that by 1.25, just like with the load side connection. Make sure that your conductors are sized to carry the current that's coming from the inverter. This is extremely important. You definitely don't want to have undersized conductors. And you can verify that it is correct by looking at the conductors themselves. Should be stamped on there. All wire has stamped readings. And then there's tables you can look up online, or I'm sure there are electrical code books to verify that the wire can't handle that average. The 2017 National Electrical Code states the supply side conductors in this situation cannot be longer than 10 feet. So here you have the power coming out of the inverter going to the supply side connection. This A to B, as I said on the slide, cannot be more than 10 feet unless you have additional measures in place to protect the wiring and all system components, like a current limiting device. All right, so in light of the fact that the supply side conductors are similar to the second set of entrance conductors, in this situation, as opposed to the AC combiner box, you would want the neutral and the ground to be bonded together. This is done correctly in this photo. You can see there's the bonding screw, you have the green coming in, you have the white coming in behind the bare ground wire. And then this is, this is per code. You have to have the neutral and the ground bonded in the enclosure. And also you need to have the enclosure grounded as well. Because of the down. Here's another supply side connection. The main difference here is there's no bare ground conductor. If you had a bare ground conductor, you probably not need to do this, but here you can see the conduit, the metallic conduit is bonded by these little clamps. What that does is it makes sure that the conduit is bonded and is part of the grounding system. Typically with this type of conduit, it goes into a knockout in the enclosure. That's already partially pushed through, so there's not a lot of metal left holding it on. Sometimes that's not enough if you have an overcurrent situation. it'll just melt right through that, and then it'll come loose, and then you have much bigger problems. So you want to avoid that, so you have to make sure that all of those metal conduits are bonded. Here's some of the labeling requirements for this type of connection. You have the traditional electrical shock hazard sticker, or it could be applied to, I guess. You have the PD disconnect label as well here, where you're going to want to have the AC output current and the normal voltage listed. One thing to keep in mind is you should not have, these shouldn't be put on and then have these values just written in, because I mean, these systems are rated to last for 25 years. 25 years down the road, that's going to be faded. You want to be able to read it. You want to have something that's either printed or like a plaque that's obviously going to last 25 years. So that's just, something to keep in mind. You don't want to have just written labels. The PV part of the code is pretty stringent. It's one of the heaviest requirements for labeling in the electrical code. So you definitely want to familiarize yourself with that part of the code. All right, so which of these options is not an accurate description of PV's system? I'll let you read through and you can just tell me what you think. And obviously, Zoom people can put it in chat. That is accurate. Yeah, so a capacitor diverter, it's not a real thing, so you definitely not want to use that when you're designing your PV system. So don't do that. All right, now we'll go through some of the labeling requirements. Like I said, the code is very stringent in labeling for solar. It's a section that a lot of us don't get right. So it's important to make sure that they're all there, make sure that everything is correct. Things you want to keep in mind are you want the labels to be able to last the length of the system, right? You don't want to have to keep having the homeowner need to put on new labels. You don't want to trust the homeowner to do that also, because they don't typically are not electricians. And you want to make sure that they're placed in manufacturer recommended areas, not covering other labels. Colors are predetermined by ANSI and OSHA. You have to use the correct coloring. Very, very stringent. Solar labels are typically yellow, orange, or red. So that's something to keep in mind. And the other main point for this slide, I would say, is the most dangerous label is not a missing label, it's a wrong label. Obviously, if you're missing a label, that's bad. You want to have it all, it's all for safety, so you want to make sure that they're all there. But if you have a wrong label, that will give someone the impression that they know what's there and they know what hazards to be looking for. And if they're wrong, they're not looking for the hazard that's actually there. So that can that will give someone a sense of security that they shouldn't have. And it could cause a much bigger problem. So it's very important to keep that in mind. So now we'll go through some examples of labels for solar projects. Like I said, all of the PV signage is yellow, orange, or red. It's easily identifiable for electricians and code officials. All right, so here's one that probably seen. It's in electrical equipment. It's on switchboards, panel boards, control panels. Basically, everywhere there's electricity, it's the arc flash warning label. It's very important because where there's potential for arc flash incidents, there's potential for serious injury or death. So obviously you want to make everyone aware of that. Here's a service disconnect labeling. This is very important because this could be the first indication for an electrician or someone, working on your home that you do have PV, right? Say someone comes in the front door of your house to work in your house on the electrical. Your PV system's on the back. They don't see it. They have no way of knowing that you have one, right? So then they go to open up your electrical panel. If these are not here, they would maybe not know that there are two disconnects. And it's important to label them, and it shows the location of the other one. Also on the label, that's so that they come in, they need to work in your panel, they shut off the service disconnect, which they will do all the time. And then they know where to look for the second, the solar disconnect. All right, so for a supply side connection, like I said, just in the last slide, we're gonna drive this home. You want to have a label, preferably a plaque or something very permanent, at each disconnect. And you can have, like on the previous slide, you can have a label where it is, or you can have kind of a map showing, here's this disconnect, the other one is right around the corner, right? So it's important for people working on your house to know where the disconnects are so they can easily create an electrically safe work condition and not put themselves in danger. All right, so on the NEC, National Electrical Code also requires these markings on PV systems. Like I said earlier, electrical shock hazard, and also the disconnect labeling, whether it's AC disconnect or DC disconnect. Again, if you, in a normal situation with no solar, if you shut the disconnect off, you have no power, right? If sun's out and you do have a solar system, you shut off the service disconnect, you still have power, right? And if you're not expecting that, that's potentially fatal. And so it's very important to label those, like I said, and the labels should last the life of the system. Again, you need to have electrical shock hazard labeling on all of your switches and circuit breaker panels, so people understand there's a hazard. This is an example of that. Anytime you have an inverter output, that's known as an interactive system point of interconnection, and you have to have a label with things, the rated AC output current and the nominal voltage. Again, my server doesn't allow writing on these labels. You need to have it printed or a plaque, so that in 25 years, when the system is still hopefully running, it will whoever's looking at it can easily read it. I think I mentioned this earlier. Also, that DC conductors coming from solar PV arrays have to, or from anywhere really, they have to be in metallic raceways that are all part of the grounding and bonding of the system, and it has to be labeled every 10 feet with this thing, this label. A lot of people don't like this, as you would expect. It's not the most beautiful of things, but what people typically do to avoid this is they'll just run the wiring through the attic, and no one ever sees it. Or you can use microinverters to basically, it just turns the current to AC current, and you don't have this labeling issue. So with DC current, PV power source label has to be on an inverter or an integrated DC disconnect or DC combiner with a disconnect. It gives important information on the system. Like it says here, you need to have the max voltage, max circuit current, and if you have energy storage installed with it, which I don't think typically a lot of people are doing, but it's possible. You have the max rated output current of the charge controller for the energy storage. And that's all, again, you want to print it, you want it on a plaque or something permanent. Here's an example of the required labeling, the interactive system point of interconnection. You need the AC current, just like on the other slides, which I think we've already gone through this one. And you need the AC voltage. A lot of times these are missing or incomplete or just not suitable for the environment. Make sure that they are. Make sure that they're in the correct location. They're not covering other labels. You know, obviously, all of those things would be bad, so you want to make sure that they are not happening. The 2017 electrical code expanded labeling requirements for rapid shutdowns. So you have to have rapid shutdown labeled when you have it, which it should according to code. Sometimes in New York City, they've adopted an earlier electrical code that doesn't include rapid shutdown. But NYSERDA incentivizes the system so they can specify that rapid shutdown is installed, or that you install according to the electrical code that they accept. So basically, in New York City, they may argue that a rapid shutdown is not required due to the code that they accept. And NYSERDA could say, you have to do it because if you want the money, right? I mean, you could install it and just not get the NYSERDA incentive, but since most of these components come with rapid shutdown anyway, I don't know why this would be a big issue. But that's just something to keep in mind. I don't imagine anyone in Albany is going to be inspecting New York City systems anytime soon, but you never know. All right, so at the point of interconnection, you have to identify all the source of the power supplied to the bus bar or the conductor. This is very similar to what we just went through. And this, like I said earlier, it could potentially be the first indication for an electrician that you have PV installed on your building. So it's important to have that there, make sure that they see there's a second source of power. So they're not assuming they're in a safe condition and they're not. Here's another label fired by the electrical code and OSHA. It's obviously self-explanatory. Just very similar to the ones we just went through. Just tells you to turn off both sources of the power before you're working the panel. Here's the power source output connection label. This identifies where power is coming into the panel. You obviously do not want to relocate this. I've already mentioned with the 120% rule and bus bar ratings and everything, you want it to be on the opposite side from the main disconnect to avoid having a lot of current in any part of the bus bar. So you need to have this here and show that you should not be relocating this circuit. Here again, see identification of circuits that we saw before. This is an electrical code issue. It's not necessarily just PV, but you know, it's of interest to everyone to have their electrical panel labeled correctly so that you know if you have to do electrical work on your house, you don't turn off the wrong one and assume you're safe. All right, so which of these options does not describe a PV warning label? Red with white text, orange and white with black text, orange with black text, or green with white background with black text. Green, yes. Yeah, all solar labeling is, or at least all that I'm aware of, is red, orange, or yellow. You will not see a green label for solar PV. All right. All right, so now we're gonna go over like a couple slides about photo inspections. Can a good comprehensive photo or inspection be done using just photos? Yes, they can. My sir has done it many times. But it's very dependent on the quality and quantity of the photos that are supplied, so. Systems can fail an inspection based on. Even if it's a perfectly installed system, it can fail if the photos that are provided are not good or. There's not enough of them, right? Because you have to be able to verify that everything was installed in a code compliant manner safely. And if you can't do that, then you have to fail the system, right? But then you follow up with an inside inspection. And you can adjust, but that's just something to keep in mind. They can help people avoid having to be on site for 4 hours inspecting all parts of the system. NYSERDA has been doing photo inspections for a long time. Permitting authorities can choose to require photos to supplement the in-person inspection. That helps them avoid making multiple trips to the site, save time and money. Obviously, you know, if you have trenching or you have some wiring that's going to be going into a wall, you don't want to have to go out to the site just to inspect that before they close it up and then have to go back out, you know, multiple times to check different things. The photos basically will tell a story of how things were constructed. Can save the inspection time, like I said. It can improve inspector safety because, like, you know, you get a photo of the inside of the panel once things are installed, and the person doesn't even have to open the panel when they're doing the inspection. You can have photos of the PV arrays once they're installed, so that someone doesn't have to go up on a steep roof and potentially fall. Things like that. So there's a lot of benefits to having photo inspections and having a lot of photos submitted with the permitting. Yeah, and you can do a full inspection using only photos. That's kind of the main point. So, like I said, NYSERDA has implemented this with great success. It helps save money, helps keep inspectors in safe conditions, you know, saves time. It's a very useful kind of program that NYSERDA's go forward and provides guidance on. So what are some reasons to use photos? Supplement inspection. I will let you guys read that. Yes. The answer is D. Can do all of these things. Can tell a story of how everything was constructed, improve safety, avoid trips to the site. I think we've gone over these kind of ad nauseum, so let's move on. Now we'll get into some common installation errors that you can see when doing inspections. Here's something we've talked about several times, but here's kind of an actual photo of it. This is the situation where you have integrated bonding of the PV system. This is done correctly, but a lot of times it won't be done correctly. You have to make sure that there's a good grounding path through the whole system. If it's not grounded, it can cause, again, serious injury or death. Now they have some panels that are plastic framed, and those they don't need to be grounded, but even if they're plastic framed, you have to make sure there's a good bond path through the system. And as I've said many times, the grounding and bonding of PV systems is extremely important. It provides a path for fault current to get to an overcurrent protection device or fault detection equipment. You know, it's super important to avoid unsafe conditions. And there are other methods that you can use to bond all this stuff. Like I said, ground lugs, you can have different types of washers to accomplish bonding. You know, there's many kinds of ways to do it, but make sure that there's a good path throughout the whole system. All right, so here we have a situation where a contractor used, I believe it was aluminum grounding lugs with a copper wire, or it's a copper ground laying lugs with aluminum frames, sorry, on the panels. What we have here is corrosion due to different metals being in contact. As you can see, this is not going to be code compliant because the grounding lug is completely removed from the panel. And this can happen extremely quickly. This happened between installation and when the inspection took place. So, you know, the screw had already corroded to a point where it snapped off and completely disconnected from the panel. So if you don't use weather rated equipment, it can cause issues very quickly. You want to make sure that that all the equipment for these systems is rated for outdoor use, because you know if not, it'll fail. And you can see up here even hopefully you can see these. There's corrosion right here between the aluminum frame and the grounding wire. So eventually, probably this whole section would be disconnected, and this panel might not even also be connected into the grounding system. All right, so here's a situation where, like I said, all the equipment throughout the system has to be grounded and bonded. You may have to look at the grounding on the racks. Here's a system where this would fail. It does look correct, but you have a ground lug installed in the rail. It doesn't pass code because the screw used to hold it onto the rail, it has two courses of thread. You have to have two threads, I guess, that is attached to the metal of the rail. This is just like a self-tapping screw, so it's pretty thick or pretty coarse threads, and it doesn't contact enough. This is to make sure that there's enough surface area for current to move through that. But this would fail based on that one screw, so that's an important one. Another very common error that you'll see is where you have wires hanging down on the rooftop. They're supposed to be supported. This protects the wires. This, you know, just dangling down on the roof. Roof shingles are very abrasive over time with wind and rain and ice and everything. It could cause damage to the wires. This could potentially make an unsafe condition. You just have bare conductors touching your shingles. Also, you may get like leaves and other debris getting caught in the wires, causing drainage issues, and you have leaks in your roof, things like that. And also another very common thing is squirrels and other animals will nest under these because they're out of the rain and they get pretty warm in the sun. So what you want to do to avoid that is there's what's called, I guess, critter guards, so that basically metal or plastic mesh that surrounds the array and blocks animals from being able to get under there. So that can avoid that problem. And they also like to chew on the wire. So you obviously don't want that. So you want to keep them away from the wires for your PV array. Talked about this before. You have to have DC rated and specifically PV rated fuses in your overcurrent devices. Residential has to be 600 volt. Commercial is 1000 volt. You have to make sure that everything is rated for PV because it's specified in code. All right, another common error is improper fitting use. You can see here Let's see. This fitting, the opening in it is much larger than the wire, so it won't provide the strain relief that it's supposed to. And then the wires flop around it in there, it doesn't provide the rigidity that it should. And also, sorry to come from the picture, but if it's raining, water could just, follow this wire right down into that junction box. Causing obviously problems, on water and your electrical. And over here, you have several problems. You have the wire nuts used are not rated for outdoor use, even though this is in an enclosure. It's on a roof. It's going to be the same temperature and humidity as the outside air. So it's essentially an outdoor environment. And also, this contractor should have run the wires through one of the knockouts and use the fitting. Instead, they just tucked them up underneath the cover, which is obviously not optimal. So they would want to redo that. That makes it so you can't get a good seal on the cover, and it's just out to code, right? I mean, you have to make sure that everything is installed correctly. Anyway. Here's another example of corrosion of bare wires. This can be kind of mitigated through using covered conductors. You can see up here, it's starting to corrode. It's not super bad yet, but eventually it'll just corrode right through and then it'll be disconnected. Then over here, you can see it much worse. The bare copper wire is corroding. Like I said, you can use covered wires that would clear that up, or insulated conductors. And that's because of contact with dissimilar metals. That will always happen. Here, same problem. You can see it's corroding where it's in contact with the conduit. That's actually copper grounding wire. Eventually, that'll corrode through. It won't be connected to the grounding system. And also, you are, according to code, you're not allowed to run grounding wire on conduit. I think you're only able to run communication or like data wiring along conduit. You can't. It's very stringent on what kind of wire you're allowed to run along conduit. Here we have a situation where the wiring is not protected from physical damage. See, there's the racking is fairly sharp, and then it goes around the shingles of the roof. Over time, it's like all these things. Over time, it'll wear through the insulation of the wire, and then you'll have bare copper wires or bare conductors exposed to the elements, and can cause all kinds of problems. So this person should have installed conduit to run that through, but they didn't. All right, so let's walk through some problems with the enclosures themselves. Code allows for the usage of what's called a leak hole, which is it allows water to exit an enclosure if it gets inside of it, right? So you can see here the rust line forming in here kind of ends at the leak hole. That means this is working properly. That somehow water got in, and but it was able to drain out through the leak hole. Obviously, you do not want this to be sealed. The whole point is to stay open. So make sure that they are not sealed. Make sure that they are installed in situations where it can be beneficial to avoid having electrical wires in standing water. Here's another kind of interesting situation. There's an outdoor rated enclosure, which is the junction box. And you can see ice that formed in the bottom. So obviously water got into those or into that. The way that you can't see in the picture, but the way that it got in is this top entry point is not properly sealed, so water would drain in. And it would just pool in here until it got up, so it could, exit through one of these two conduits. And then you have just water throughout your whole system. Which, as I have mentioned many times, is bad. And this could have been avoided with a weep hole, because, you know, you have water cooling, it'll be pulling the bottom, it'll strain right out. But obviously you want to fix that, that connection that is not properly installed, so that you don't have any water getting there. Here we have an enclosure that not only has water, you know, standing water inside of it, which I would never tell you is a good thing, obviously. It is also, it doesn't have outdoor rated equipment installed. You can see the wire nuts used are not outdoor rated, and specifically this ground lug and the screws are not rated for outdoor environment. They're rusting, eventually they're going to snap right off. And then you have, you know, an on-ground system. And then over on the right, you have these two are pictured the same thing. This is close up. This is a flat roof with solar panels on it. And someone put a conduit coming out of this enclosure that is pointed up to get over the racking. What happens when you do this is when it rains, the water will just go right in, and then it drains into the enclosure, causing problems, obviously. So you want to keep your eye out for that, for situations where rain can get in and you know, pool in an enclosure, or get in any kind of contact with electrical wires. Here we have conduit passing from the outside to the inside of the house. This is actually an energy code issue as well as an electrical issue, because what happens is cool inside air or cool outside air, I guess, goes in or out, and it'll have contact with much more moist, warm air. What happens is it condenses on the wires, it will just drain right down the wires. And then it'll go into your house, right? So into the electrical system of your house. So you don't, that's something no one needs. And you want to avoid that. So to fix that, you would seal this penetration with like insulation, to avoid the airflow. All right, here we have an example of this you can't tell really here. The inside of this enclosure is metallic. The outside is plastic. You have metal conduit coming in. You have to make sure that you have good bonding between the metal conduit and the inside of the enclosure. You know, for code, you have to have grounding throughout the whole system, as we've mentioned many times. So that's the problem there, potential problem there. You can't tell from the picture. But also, you have this wiring that it's not really supported. Another thing maybe you want to have some fixed. All right, here we have a disconnect that was installed incorrectly. Someone's using a non-contact voltage tester. We can see this disconnect is open, so you can see, and you still have voltage on the bottom of the disconnect, right? So that means that the service connectors were installed on the wrong side. These fuses will always be energized, so you can never safely change them out if something is bad. So to fix that, you would have to switch the conductors from the bottom to go to the top. And then once you disconnect it, the fuses are non-energized, and it's safe to change them. Another thing to keep in mind when you're inspecting is if you are using one of these non-contact voltage testers, sometimes they don't work on DC voltage. So you have to be extra careful. Don't only rely on that, because it could just not be working. Here we have a supply side disconnecting situation as this is actually done correctly. You can see right here, you have the neutral and the ground coming into one grounding plug. And it's done by the use of this screen ground screw. They're connected together. This is the situation where it's essentially like a service disconnect. So this is a situation where you do want the neutral and the ground to be bonded together. Here is a situation where we have multiple wires that are terminated in these. Sorry. These connections, sorry. So these connections are rated for a certain number of wires, a certain size wire. In both of these situations, you have multiple conductors being terminated at those conductors or at those connections. That's not what they're rated for. This should not be done. It's not super safe. And also you want to make sure that the conductors that are supposed to be there are within the size requirements of that, the breaker or the connection, the lug, whatever. For load side connections, like I mentioned, many times you'll see situations where the labeling is not done correctly. You want to make sure that all the labeling is correct. In this specific situation, it's showing that there's another power source. You don't want to relocate the breaker. That's a back feed breaker, and then it has the PV disconnect information. You want to make sure all that's there. Here is a situation that's not very common, but it's what's called a feeder tap, and it's a type of interconnection that you need to specifically look at. It's kind of a hybrid load side connection, so it has potential to add available current to conductors or bus bars. So you need to consider that. You need to potentially put in additional overcurrent protection with the right here. It's an extra breaker to, if too much current is being pulled through, then it'll trip and not allow that. Here's a picture of that in real life. You can see that the interconnection on the load side of the 200 amp breaker for the apartment. This is an apartment. An apartment panel doesn't have a main breaker, so they install an extra breaker, and then this is where the feeder taps are located. They have another disconnect needs installed so that the bus bar and the electrical panel are not overloaded. Here we have a situation where the flashing, or not the flashing, the seal provided is not done correctly. This is what you would want to be used. This is using duct seal, which is it's fairly waterproof, but it over time with the grade and stuff, doesn't look great. It's basically just putty that goes around the hole. So you don't. This is not correct. We want to use one of these. This is the situation where the earlier in the presentation there was the one of these that was pushed down. So you want to not only make sure that this is used, but make sure that it's installed correctly. Oh, this is an interesting. This is a situation where this electrical panel was installed outside house. And obviously, I'm assuming that you can tell there's a big difference between these two conductors coming in. And this lug itself is very discolored. So what happened here is these two conductors were connected. This one was not installed correctly. It's not torqued down correctly. So It didn't have a good connection with the conductor, so it would get hot, cold, hot, cold, hot, cold. And eventually it burned off the insulation of the wire, which is obviously not good. And then it's outside, so there's moisture in the air. And it causes corrosion of the wire. The corrosion causes it to fleck off and land down in the electrical panel. As you might imagine, this is not good. So what happens is the only way that they could fix this was they had to completely tear the whole thing out and put a new one in, right? So make sure that all the lugs are torqued down. Obviously, look for discoloration of these things to kind of double check that. Make sure the installation is good for the wires, things like that. So you can avoid this kind of situation. Only like 5 slides left. So here's a situation where there was a natural gas explosion. It's outside Boston. And this person had a solar system on their house. You can see the house is it's in bad shape, as you might expect. But the roof where there was solar PV, it's fairly intact. This is not, this is obviously not a problem with the installation of the PV. This is just kind of an interesting situation where some people think that the racking systems used for solar PV actually strengthen the roof, and this is kind of only one piece of evidence, but it's some evidence of that. You can see, like I said, the roofing is fairly intact. It's just kind of an interesting case study on there. I'll go through a couple new products that are kind of available, or they were new when this presentation was made a couple years ago. So this is something that's called Connect DER, Distributed Energy Resources. It was being used in the Con Edison territory. What it does is it installs in your meter pan, and it provides the utility with data on like how much solar you're producing, or the homeowner is producing. And it also allowed interconnection to be completely outside the home. So when you were having solar put into your house, people didn't even have to come into your house. Everything was done all outside the house. That was handy. And what they do with this solar data is they can use it to kind of project what will be produced at any given time to help kind of balance the grid and all that. So it's kind of interesting. Here we have a micro flashing. So these are used basically to anchor the racking system to your roof. Typically, you would want a roofer to deal with the penetrations of your roof, but maybe this may be helpful for like an electrician. They're putting in the racking. I don't know if there's any real data on if it is actually helpful, but it could potentially be helpful, and you might see them installed all over the place. There's additional resources, like I mentioned, like 12 times. It sort of has a lot of stuff that you can reference. There's the book, the solar guidebook. There's the energy storage guidebook. All sort of reference guides and checklists, all kinds of stuff. You'll have this slideshow available for you. You have links for this if you want to check those out. They can be super handy, especially the checklist. They can, it has all the code references and all that, so it's just super handy. And then here is kind of an interesting picture. It's here we have a high school that has a track and field, and they installed a 1.2 megawatt solar PV system. Next to the school. You can see that the PV is a little bit bigger than the track in the field, but it's just a good kind of visual way to show the size of these systems. A 1 megawatt system would be about as big as a track meet. So that's that. If there's any questions, I'm happy to take them. And if you think of any questions after this session, then you can email me. There's the my email, which I showed at the beginning, and it'll be in the presentation that's provided to you. And also, like Jen said, she was the previous instructor. You can email cleanenergyhelp@nicerba.ny.gov for questions. So yeah, if there's any questions, I'd be happy to answer.
Not really a question, but more of a general statement. So in our town and many other municipalities, we require a third-party electrical inspector to inspect a lot of those items. So this has been very helpful to us. We don't see that stuff all the time because the electrical inspector is actually the one inspecting those connections and everything else. So for us, we look at labeling, making sure that third-party electrical inspector is signed off, a couple other items. So it's been very helpful to us. So thank you.
Oh, good. Yeah. Appreciate it. Helpful.
I did not know that the labeling cannot be handwritten. So
Yeah.
we'll be looking for that.
Yeah,
I-
like
I
20
know
years
it.
down the road, it's just gonna be like, what did this say?
Yeah, exactly.
Like,
So thank you.
I'm glad it's helpful.
Okay.
Anything else, anything in the chat or? Awesome. Great, well, thank you guys.
I just want to say thanks for you guys for attending and everyone who attended on Zoom. Appreciate you coming out and feel free to reach out if you have any questions. You guys.
Thank you. Chris.